Here's a tough question from number theory. Given a prime number p that is greater than 2, prove that the numerator of s is a multiple of p. Here, s is the sum of 1 divided by 1, plus 1 divided by 2, plus 1 divided by 3, and so on, up to 1 divided by p minus 1. I'll give you a moment to pause the video and think about this. Done? Then, let's get started. Okay, if you tried working this out directly, you probably noticed it's not easy. So here's a clue. Use Wilson's theorem. Take any prime number, let's call it p. Now multiply every number from 1 up to p minus 1. That's called factorial, so we write it as p minus 1 factorial. Wilson's theorem tells us that this factorial is always 1 less than a multiple of p. Or, in other words, if p is a prime, then p1 factorial is always equal to negative 1 modulo p. Try to remember that. It'll useful later. Now, back to the problem. One thing we naturally do when we're dealing with a sum like this is try to equalize the denominators. Why? Well, fractions are messy. They're hard to work with. And more importantly, the question only cares about the numerators. So what do? We look for a number, a clean, simple number, that's divisible by every denominator in sight, 1, 2, 3, all the way up to p minus 1. And that number, that's p minus 1 factorial. So let's try to equalize the denominators and see where that takes us. Now let's label the numerators with a and denominators with b. Now, our goal is to figure out whether a or b is divisible by p. And one really useful tool for that is to work modulo p. But before we jump into that, let's zoom in a little on a and b. Remember Wilson's theorem? Now take a look. Both a and b actually contain p minus 1 factorial. That's our common denominator after all. So let's apply Wilson's theorem to b first. We get b is congruent to minus 1 mod a p, which tells us something super important. b is not divisible by p. That means if the whole fraction a over b is divisible by p, it can't be because of b. So the only way for s to have a numerator divisible by p is, well, if a itself is divisible by p. Now, let's try to apply Wilson's theorem to a. That's interesting. Our a become very simple. And that sum you see? It's just a sum of modular inverses. But here's the beautiful part. The set of all these modular inverses is just a rearrangement of the numbers 1 through p minus 1. Why? Because modular inverses mod p for prime p are always unique and exist for every number in that range. So you can think of it like this. We're summing all the numbers from 1 to p1 just in a scrambled order. And to prove that, let's say we pick a and b from the set of all integers less than p. Our goal is now proving that no two number have same inverse. And to achieve that, we'll try to prove it by contradiction. Let's try to pick two different numbers from the set. Let's say a and b. Now, we'll assume this a and b have same inverse modulo p. Now, if we multiply both sides with b, and then multiply both sides with a, we will get b equivalent to a modulo p. But that's impossible. We started by assuming that a not equal b, and now we've just shown that a equal to b. That's a contradiction. So, what went wrong? Nothing, actually. The logic was solid. It's the assumption that was wrong. Therefore, no two different numbers in the set can share the same inverse modulo p. Now, the easy part. Since all modular inverse of 1, 2, 3, and so on until p1 is different, as I've told before, the value of a is sum of all the numbers from 1 to p1, just in a scrambled order. That means the value of a is just an arithmetic sum, p minus 1 times p over 2. Now here comes the neat part. Since p is a prime number greater than 2, that means p is always odd. That's means a modulo p equals 0. That's mean a is divisible by p. And just like that, we just solved the problems.